Introduction to Network Analysis, Methodologies, and Tools. Who I am, I'm Ryan Horn. I'm a research consultant here at OARC, and we are trying out the new OARC Zoom room and podcasting facility, so that's why things might be a little bit blurry or a little bit green screening, etc. So let's get started here. What we're going to do today is I'll give you a quick intro of network analysis things. We'll talk about some data practices, and the whole time we'll be doing about really getting into network terms and concepts and what social network analysis is. And we're going to be hands-on with Python, Gephi, and Gephi Lite. There's a little bit of that should be a common instead of an M. My apologies. And if you see the QR code here, you can actually download the presentation and have access to it from my Dropbox. Some of the tools we'll be using, you can grab any one of these, download it as the presentation goes, or just follow along and see what's happening. One tool, a very popular one, is Gephi. It's an open source tool. It's very easy to get a network built and started in this thing. The problem is that it needs Java, and it is sometimes very wonky. I've tried to teach courses using Gephi before and have spent most of my time doing Java installs and tech support. So it's there, it's interesting. It is in a perpetual beta state. I think it's on like version 0.1 now. So just keep that in mind. There's a very new thing. This is, I believe, only 2 weeks old or so, and this is called Gephi Lite. And it has all the things about Gephi. It's open source, it's wonderful, it's easy to use, but it's a beta of software that's also in beta mode. So if you want to think of something like Inception, this is, a beta of maybe working, maybe not working. Not everything that works in Gephi is working in Gephi Lite yet. It doesn't even import CSV files. It has to import Gephi files. It is an interesting option, and it's one that I think you should keep your eyes on if you're interested in social network analysis and don't want to get into, say, Java and all that kind of mess. And again, you can find the link here, or the QR code will take you to it. A final thing that you want if you're using Gephi Lite is this CSV to GEXF format converter, because again, Gephi Lite's not ready to read CSV files. And you can find this website will take you to that. So just a heads up if you're going to be following along with the CSV files here. And we're also doing a Google Colab book. And so I have this launched here, and you'll see that, okay, it should open on its own. There we go. And I will post the link to this in the actual chat. And this is if you want to follow along and see some of the live Python code as we go. So I will go ahead and put that in our Zoom chat. Another thing you may want to look at is the data that I'm going to be using as an example. Don't read the data too much. Some of it will be a surprise, but that's where you can download it and access it. So what is a network, and why are you actually here? What are you interested in? Basic idea is that networks are a collection of entities, of stuff. It could be people, it could be concepts, it could be cells, it can be computers, what have you. They're things that are, at least some of them are linked to each other. And that link is kind of up to you. Is this a physical link? Is it a conceptual link? Are they people who attend the same karate club as the famous example? And these are all kinds of subject domains. And it's a very flexible definition. Once you start thinking about networks, you'll probably find networks everywhere. There's been a lot of interest recently in social network analysis for fields like historical analysis, or things like, again, social sciences, or even just physical computer networks. And you can see it's used for, again, people. You see in literature, biological systems, there's a lot of network analysis used there. And again, electronic systems, like how do you actually network computers? So it's networks upon networks. So what is social network analysis then? We want to see how the data relates to itself. How do we look at how things are related? How are they connected? How does this whole kind of system that we're conceptualizing work? Where do you sit on it? Where does your data sit on it? And that is what social network analysis is essentially. Here's your entities, here's how they're connected. Now we're going to do some mathematical modeling. We're going to actually describe this network in a way that isn't just, hey, these things are related. And so if you want a very formal definition of it, it's a method to perform visual and mathematical analysis of relationships. And for this to actually be any kind of field of study, our analysis has to be both visually interesting and useful to some extent and mathematically rigorous. So everything I'm showing you here, there's actually math behind it. There's logic behind it. We're not just making pretty pictures and throwing what we like to call the spaghetti balls of doom out there so that no one can understand what we're doing. The idea is to communicate what a network is to actual people. So having said that, here's what we would call a giant spaghetti ball of doom. Just go ahead and put a giant thumbs up if you understand what is happening if I put this graph in front of you. If you don't, go ahead and put a red X or some kind of panicked face. No idea. Very good. I don't have any idea what's happening here. Some confusion, lots of overlapping groups. All right, so there's something's going on here. To me, it kind of looks like a disastrous attempt at a tie-dye shirt. Like, this is not a very easy thing to show people or to get a lot of meaning from. It's a kind of a mess. But it does show there's connections and groups, but generally you're not going to communicate much with a lay audience or even an audience that's very familiar. Yeah, Jackson Pollock. Right. This could be you can frame this and put this in your house somewhere. What about this? Someone tell me what's going on here? I mean, you can just read that too, but we've got some ideas of airport hubs, daily flights, communication systems. What this is actually a representation of users connected to other users on Facebook. And it's just a network that we said, all right, here's where a user's theoretically located. Here they're connected to all their friends, and you can see all these different paths and lines going across. So this is a geospatial network. And all it is the same kind of thing that we just saw. So this kind of thing, only instead of having a random algorithm, we've put users in places and we've connected them with these lines. Is this something that is a little more understandable? I mean, do you look at this thing and say, hey, I kind of get what's going on here? Or is this something that you're going to be like, hey, it's just still a bit confusing? I see an emphatic, yes, I understand this. See, this is a graph that communicates something. And it's a really interesting graph too. You can see where Facebook is very heavily used and where Facebook is not used at all. And of course, you can see the famous night maps. You can see South Korea and not a lot of Facebook users in, say, North Korea. Having said that, here's another great graph. And this is another one I think that's actually fairly useful. This is from Game of Thrones. People still are familiar with that, right? This isn't a completely outdated pop culture reference. People know Game of Thrones, I hope. Couple thumbs up, good. I show this stuff to my students and I realize I'm their parents' age now. And so everything I've got is probably way out of date. So we've got Game of Thrones. There's going to be maybe some alerts for Game of Thrones coming up here. But what this represents are characters within the actual book. And the connections are how many times they share pages with each other. And again, this is something that this is a much easier network to look at, right? It's a much easier one to understand what's happening here. And we've got different kinds of color groups here. And those are communities. And we'll get into that, what that actually means later. Another way of using networks, and this is something that's been increasingly used, is within the military context, especially since September 11. You can see here the Army's counterinsurgency manual actually talks about social network analysis and how people are connected to each other and how they're actually looking at social networks. So this is something that's being used in business, something that's being used in geography and in education, and something that's also being used by the military industrial complex. So the idea is, again, networks are everywhere, and there's a lot of actual use of these things. Any questions so far? It's always hard to gauge on Zoom if people have any questions or issues. No? All right, so we'll move on. And let's get into some basic terms of networks. So nodes, edges, and graphs. And if you've heard these before, go to your happy place for a little bit. If you haven't, let's get into some of the terminology that's generally used. In terms of nodes, what are nodes? This is the stuff you're looking at. So a node can be, again, a person. It could be, in our Facebook example, a user. It could be, say, a cell type or something else. It's the stuff that you're looking at. It's the actual entities, the things that you can say, hey, this is a thing. And when you're doing network analysis, these entities can have any attributes you want. So you can say, oh, if they're people, we can do, age, we can do education level, we can say favorite food, color shirt they're wearing. It doesn't matter. You can have as many attributes as you want. And these are traditionally represented by the circles on a graph. And so you'll see that when we're looking at network analysis, we're looking at networks like, say, this one, the nodes are the people. So like Jon Snow is a node, Tyrion is a node, and again, it's circles. You may see the term actors used. I prefer nodes because I think actors gives a little bit of agency to the thing that it might not have, especially if it's a conceptual network. But again, you may see actors used in the wild, so so you know what it is. Edges are what links are nodes, and these are also sometimes called links, very imaginatively. And it's kind of up to us to define what is a link. So if we think about like the context of this workshop, everyone here is a node, and we're all linked to each other because we're in the same workshop. We can say links can have weights. So maybe you have, say, two cities that have a lot of economic traffic between the two of them. You'd say, oh, this has this link has a large weight of our economic value, and maybe between another two cities, it's a smaller weight because they have smaller economic values. These are generally the lines on a graph. And so again, if we go back to our Game of Thrones example, the edges are here. These are the links between the nodes, and the wider ones are showing again that they're on more pages together. So that would be the weight of these. A graph is mathematical models of network structures. This is what we're actually showing. And believe it or not, there are rules. We can have really messy graphs, we can have terrible graphs, but when we're actually generating them, this is due to mathematical principles that our software is using. So we're not just randomly throwing nodes out there, throwing lines out there. We actually do have rules. Then, and if you haven't seen The Big Lebowski and you don't know this scene, please do so after the workshop. Okay, well, what kind of graphs are we dealing with? The standard famous graph that you're probably going to encounter most of the time, or make most of the time, is something called an undirected graph. This is where the relationship, the direction between the two nodes, it simply doesn't matter. So we're saying that, like, say again, this workshop, if you're attending the workshop with somebody else who's attending the workshop, there's no directionality to that relationship. You're both in the workshop. They don't need any arrows. You just have a line that connects the two things. And this is really default for a lot of social network analysis. Let's go back to our Game of Thrones example. If we have a connection here, we're not saying that, John and Samuel, that there's any directionality of that relationship. It's just that they are mentioned on the same page. Directionality doesn't make any sense in that case. And so if we have, again, like Rob and Caitlin here, we're just saying they share pages together. Does that make sense to everyone? That's an undirected graph. You're just saying two things related. It really doesn't matter how we're conceptualizing that relationship. It just happens to be there. Now, sometimes though, it's not enough to show that. Maybe you want to say that A is related to B in a certain way, but not the other way around. And this is what we call a directed graph. And this is where we're saying like A to B means something that B to A means something different. To go to our another Game of Thrones example, this one is actually put out by HBO. This is a kind of graph where it shows directionality does matter for some of these things. Now, you can see here, allies, that's just an orange line. That kind of concept, they're just allies. The directionality doesn't matter. Killed does matter. And again, spoiler alert, we can say who's killed whom. Well, Eddard has killed Arthur Dane, not the other way around. And so you can see the directionality matter here. A parent, that matters, right? Who is whose parents? Again, massive spoiler alerts for this graph, but it's been several years. So you can see directionality does matter for some contexts and it doesn't for others. And later, when we're talking about paths between nodes, that's where this really comes to play, that you only have certain directions you can go if you have a directed network. And this also becomes important if you're thinking about things like information flows or movement through, say, highways or other kinds of physical networks where directionality might be very important. Like a one-way street, it only goes one way most of the time, right? Or these kind of relationships, again, only go one direction. Everyone with me so far on that? All right, I'm not seeing any red X's or any confusions. So again, feel free to throw up a red X or throw a message if you want me to slow down or cover something else. And so what about data? How do you actually use data? How do you get data into how do you formulate what you're looking at so you can do network analysis on it? And yes, it's data. Well, there's going to be Star Trek references in here too. So, basically, this is also a lesson in pop culture up to the early 2000s. And these are things to really consider before you do network analysis. The first one really is, what is your data? What do you have to look at? Do you have like genealogies? Do you have relationships that are easy to actually examine? Or are you going to have to make all of these yourself and infer things? This is pretty important because what kind of data you have is really going to dictate how you're going to look at it in the network. The other thing is, what are you trying to show? Are you trying to show a relationship that is, again, like genealogical? Then you want to have a directed graph. Do you want to just show a relational relationships? Like, oh, these people are just in the same area or they're sharing the same kind of concepts, or they're co-authors. That's going to be an undirected graph. The other big thing is, how are you going to organize your data? And you really consider, are there standards in your field? Like, say, for historical data, there's if you're looking at ancient world data, there's the standard of ancient world prosopographies, which is a way of looking at structured network data for people. This might be different for a different field. If you're doing cellular analysis, you're going to have a very different way of structuring data than somebody else. So something that's really important is, how does your field handle data? And if there are no standards, great, start making some. So think about that. The more attention that you pay to database design and data wrangling at the beginning, the better it's going to be for you down the road. So if you really think about, here's how I want to structure my analysis, here's how I need to structure what I'm pulling in, you're going to save yourself a ton of time later. I just want to do a show of thumbs up or green checks for who has used spreadsheets before. Oh yeah, tons of thumbs. The mighty spreadsheet, which is 99.9% of all digital humanities work starts here, and free pizzas for graduate students, and you've got most of your projects. So if you're building your kind of data analysis, you're going to be using a spreadsheet to get your stuff into your networks. And so I'm going to go over a few just best practices. This will probably be a reminder to most of you, but just to keep these in mind when you're doing network analysis, that you want to make a unique identifier for everything you're looking at. Generally, you don't want to use, like, for people, you don't want to use their names. You want to use something like or social security numbers. Those are unique, but you want to make your own unique ID. You want to say that each column of your spreadsheet contains the same category of data, so that, if you have a column of, say, a person's age, it's all numerical data. It's not 40 and then like 40 spelled out or something like that. You want to keep the same kind of data. Each row, again, you want one row for one entity. So if you have, say, Bruce Wayne and Batman, those are the same people. They're going to be on one row. Perhaps they have different names, but you want one row for one thing of data. And what you want to do is have column names which are unique to each spreadsheet, to the top of the row. So you want to have names that are descriptive, names that you understand. You'll probably want to do alongside when you're making a spreadsheet, a README file, because trust me, if you have column names like RD592, you're not going to remember what that means. And 3 years from now, you may not even remember what that means 6 weeks from now. So you're going to want to write a note to yourself, basically, of what your column names mean. And you want to really think hard about what attributes, what are you looking at? What are you trying to collect for your analysis? So maybe you're making a network and you want to filter it only on authors. Well, then you probably want to exclude publishers from this kind of table. The other thing is, don't be afraid to make multiple spreadsheets. You think about these as multiple tables in a database. Maybe you have one for, again, authors. Maybe you have one for publishers. Maybe you have a table for books or another table for bookstores. That's fine. Make as many spreadsheets as you can possibly need. And the other thing is, when you're making make unique IDs for each thing, which are unique to that spreadsheet. So not just an ID of one that is person, an ID of one that's a bookstore, maybe a ID that is person one and an ID that is bookstore one. And that way you can actually link them up together. And document, 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 and document. I cannot say that enough. Document what you're doing. You will thank yourself later. And when you build all of those, you're going to start then constructing your networks. And the kinds of graphs and networks that you build, we think about these as modes and types. And so modes will tell you what is in a graph. Are you making a graph about people, people and things? One mode would be people. 2 modes would be people and maybe the books that they write. 3 modes, people, books, and places, and so on. You want to generally, for a lot of graphical and data and network analysis, limit the number of modes that you have in a network. Otherwise, you start getting into strange connections and things that don't quite work with some of our mathematical models. And the types will tell you what kind of graph it is. And again, if we're looking at a group, a text, or an individual. So modes are the different kinds of things in your graph, the different types of entities, and types are exactly what we're looking at as a whole. And so if we're looking at, say, one mode or unipartite networks, these are mostly what most graphs are. Same types of nodes, same types of edges, we're just expressing a relationship. And these relationships can be different, like parent-child, again, Game of Thrones, like related to, allied to, whatever, but they're still the same. It's just the same kind of node and the same kind of conceptual relationship. 2 modes or multipartite networks, you can say different sets of nodes. Like let's say people that are working in different businesses, or people that are in different kinds of events. And this can be really interesting for things like strong and weak ties, which we'll get into later in this workshop. And a multipartite network generally looks like something like this. We'll have, in our case, U would be maybe people, and V would be, say, club affiliations. And so you can see here that these are actually kind of useful for saying, oh, who's doing what, and how are they connected through each one of these things. But it's not so useful if you're looking at a much larger social graph. So just keep that in mind between multipartite, unipartite. You'll see that this kind of terminology come up. And so now let's take a look at some of the sample data we have. This is from a external project that was looking at Game of Thrones. And you'll see that they did something that I don't like too much. They used names for their IDs, but all the same, here it is. And you'll see that we have this arranged in a data table where we have our source, in this case, Ned, target, that's who he's related to. Weight, this is the number of times, or I think it's minutes they shared on the screen together, and what season of the show it was. If you look at our data table, again, you'll see there's like 546 rows, and each one of these characters has this kind of relationship to each other. So what do we do with our data? Well, let's make a graph with it. And so if we look at, say, our Python code, and I have some live code here in the presentation, you'll see things. This is just to show you that you can do this programmatically, but you can also do it in terms of Gephi. And so that's what we're really going to look at, because, and I'll take you through Gephi in a second, and I'm going to have to do some screen sharing, switching back and forth between things so you can look at this. This is, of course, Gephi. you'll see that if we have a new project, we've got a nice little blank screen and we've got really just nothing there. And that's fine for what we're doing at the moment. So let's add if you're using Gephi, we can go to Data Lab, and we want to import a spreadsheet. And you can see it has nodes and edges. Now, the one that we're grabbing is an edges table because it's showing, again, a node and another node and saying that there's a weight for that relationship. And so if we downloaded our CSV file, which I believe I have, and you can see that Gephi has a rather antiquated interface. We'll pull in our book one CSV. And you'll see that it's right. We're importing as an edges table. We have our source. We have our target. It's an undirected one, and it actually has weight. So this would be a book graph of how many times these two entities talk to each other. So if we hit next, we don't have any time, so it doesn't really matter. If we hit finish, see, it gives us our nodes, our edges. We're going to put this into an existing workspace. And there we go. It has what our sources are, who our targets are, an ID for those. And if we go to overview, you'll see that we actually have a network graph. And then the fun thing about Gephi is you can click on it, you can do these things, you can move them around. It actually becomes just a lot of fun to hit like different kinds of ways of visualizing graphs. So we see a layout here, we can do, say, for Atlas, which is a pretty common one. You can see adjust by size, you can spread these things across, and that becomes a graph that we can kind of look at. And if we turn on labeling, if we go to our lab, we will see that it actually built our nodes table for us, but we don't have any labels. And so we would just say copy our ID to our label. In this case, if we go back to our overview, you'll see they all now have labels. And we can pull that down like this. And that becomes somewhat of a comprehensible graph, right? And you can zoom in, you can see the different kinds of labels. You can hover over it and you can see who is a neighboring node to whom. Everyone with me so far on how that works? Any questions about at this point? Nope. Cool. And if we go back to our, okay, and if you guys can still see, can you see the presentation still or not?
Yes, we can see it.
All right, cool. And so if you look at it in Python, it's a little more complicated. You got to pull in a few packages, network, in this case, network X, CSV, pandas, all kinds of, this will come into play later. You can pull in the CSV file as a pandas thing, as a pandas data frame, and then you say where you're pulling this in and saying, hey, here's my edge list, source is my source column, target is my target column, and then we just draw it with again the internal functions, and you'll see that we get a graph. Now, which one do you guys find a little more? Now, you'll see again that you get a graph that's probably a little bit easier to look at and analyze on its own within Gephi. But if you're looking at, again, Pythonic code, you can pull this thing in and do all kinds of crazy stuff with it. So it really kind of depends on where you're trying to come from what you're looking at, and what tools that are useful for you. So any questions on that? No? All right, great. And so that's just the general way that you make a graph. And so if we look at, now that we have a graph, kind of look at some of the things that can happen there. Moving in a graph, or if you want to think about how, say, information travels or how relationships go, it's via edges. So if we want to think of a graph to model something like epidemiology, how a disease spreads through things, it would move along the edges of a graph. And we can say a path is how you connect two nodes within that graph. So if we go back, and we'll use Gephi this because it's fairly easy to see. If we go to, I can get my mouse back to my screen. There, we can say like Rhaegar Targaryen there, he has a few neighbors like Robert Baratheon. But if we want to say, all right, how does he get to, say, some other person? So Rhaegar to Sansa to Arya, you see that's a path of 3. So he has to go here, he has to go to his neighbor, and he has to go to his neighbor's neighbor, and so on and so on. And so this is a measurement of graphs that you follow these paths, you don't repeat going to the same node. And that's how, and you can do this programmatically to figure out how between any two nodes, what's the path? How long does it take to get from one to another? And this is a really kind of an interesting issue when you're talking about networks, is the idea of connectivity within a network. Does every pair of nodes in a graph, can you get to another node? So in other words, is there anything that's completely and truly isolated in your graph? If you're designing a network, like a physical network, connectivity is kind of a goal. You want to be able to reach any part from any node in your network. This also becomes a goal for how it's an interesting problem if you're dealing with a social graph of, say, a clandestine organization. Do you really want to be every node to be able to reach the other part of, say, your secret society or something like that? There are social networks that have these kind of disconnected features, or maybe they're very loosely connected. And so, as an example, does anyone know what this is? I mean, here's UCLA. That's pretty cool, right? Does anyone know what this is a graphical representation of? The internet and ARPANET. That's right. The goal was that anywhere on this graph, in case one of these nodes got taken out, you could still access all the other nodes. This is the original ARPANET internet connectivity graph. If something would happen to Stanford, you can still route to UCSB or UCLA or the RAND Corporation and so on. But you can also see where are some of the key nodes here that if you did take them out, you'd break a lot of connectivity. Yeah, if you took out MIT, you could still get there through one other node. If you take out MIT and BBN, you've now suddenly created a very disconnected system. And so as more nodes were added, it was trying to build more connections between things. We're now on the internet that we know and love today, with all of its glory and craziness. And this gets to the idea of components. If you can think of components as natural breaks for connected parts of a graph. In this one, this is a connected component. Everyone has a subset to each other, but we can still think of, say, this collection as a conceptual component. They're more linked to each other than they are to over here. Or say these 4 links are much more linked to each other than these are. And so that's the idea of components. Think of them as almost communities of links. A giant component, and this is informal, we don't really have a mathematical way of saying this, it contains a significant fraction of all the nodes. So we're going to go back to Game of Thrones. And just give me a thumbs up if you just hated the character Joffrey. There's some thumbs up there. Basically, everyone who views Game of Thrones hates Joffrey. The actor did a fantastic job. Everyone hates him. Now, if we want to do in the context of the story, everyone hates Joffrey still, except for maybe him and his mother. So we'd have a giant component of people who hate Joffrey, being most human beings, and a smaller component of people who actually care about Joffrey, maybe 2 people. And so you can see that's kind of what we're talking about for a giant component, something that connects most of the nodes, but not necessarily all of them. And when you're doing networks, most of the time and over time, networks only have one giant component. They may start with like two, but as networks evolve, and they will generally form into one. And you can actually kind of find this if we're going to look at our Pythonic code. So if we go back to our graph, what we do is we do this thing called sorting it. And we're saying how what is connected to what to each other. And we're going to say for what it does is takes each one of your items in a graph and says, all right, where are all the paths? And the ones that have the most connected paths is the first graph. If there's ones that are disconnected but smaller number of nodes, second graph, another one that's disconnected even smaller, a third graph, and so on. And looking at our Game of Thrones one, our giant component, actually everybody is connected to each other. They all somehow within the actual book talk to somebody else who talks to somebody else who talks to somebody else. So we have just one giant all connected component here, which would be an idea for network design. And what becomes really interesting if you think about the development of graphs and graph theory is that as I said, giant components eventually will merge together in a graph because of how people will know each other, someone knows somebody who knows somebody, and so on, and eventually this will come together. These often really are a thing of catastrophic change, that when you have two giant components that merge, lots of things happen, lots of connections are forged, other connections are broken, there's lots of side effects. If you want to think of really one of the largest giant component mergers in human history, 1492. What happened when what happened in 1492? We have the Western Hemisphere and the Eastern Hemisphere now getting sustained massive connections. These components effectively merge. And what happens? Well, disease, massive political change. Previous contacts within the Western Hemisphere are completely disrupted. A lot of this becomes a really massive sea change in the network itself. So if you're thinking about how networks develop over time, you see different giant components. Again, these will eventually come together in theory, and when they do, they're going to have a lot of effects. Can any of you think of a similar time of maybe some kind of giant components that become connected and things become messy, so to speak? Or can you think to your own studies of something where you may have maybe an idea if there are several giant components of something you're looking at right now? If so, go ahead and feel free to put that in the chat. This is actually a really interesting concept of how networks develop. And if we're talking about components and giant components, this gets into the idea of graph distance. And we're not necessarily meaning geographic distance, although sometimes they're analogous. What we're talking about is the shortest path between two nodes. And so sometimes you can look at this. If we go back to our Gephi example here, I can say between Aragon and Eddard Stark, well, that's easy. That's one. Or Targaryen, Sansa to Arya, all right, that's path of two. But sometimes you can't, right? Do I want to do that manually for this entire graph? Does anyone want to do that manually? I'm not seeing any enthusiasm for that. So we need computers to do this for us. And the Pythonic code for this is actually fairly simple. You just say, all right, I'm going to make a dictionary out of this. This is your function call. All pairs, what's the shortest path? And the result is it gives you a JSON file saying, well, for Ned, it's himself. To Robert, he's connected. To a little figure, he spins blah, blah, blah. And we can scroll down, we can see different characters. So for Baylor, it's Robert, Ned to Baylor. Hugh, it's Robert, Ned to Hugh, and so on. And so you can see that this will actually build in Python the distance for you. In Gephi, you actually can do all these wonderful statistics here and just run them, and it'll give you like connected components, a report, and you'll see like decrees we'll get into in a second, average path length, undirected again, you'll see that it gives you all of these things, and you get those from your data lab. You'll see that we now have actual measurements that are going on there and what components they are. So again, different ways of accessing the data, depending on how you want to look at it. Okay. If you want to know how search algorithms work on graphs, and you'll probably encounter these as you do networks, it's kind of an interesting way they do it. They do an ever-expanding ring. And so this is how your algorithms work, how this graph distancing works, for instance, is it starts with a connection, goes to your neighbors, goes out from those neighbors, and to the other neighbors, and so on. And that's why it's a very computationally expensive thing to do. But if we're searching, we're looking at paths, and I'm sorry for putting this earworm into your heads for the rest of the day, probably. I could hum it, but I won't. Has anyone heard of the small world phenomenon in terms of graphing? I don't see any hands. I don't see any checks. I hear one. Yeah. Okay, there's one yes. Ah, and brain networks. Okay, how does that work within a brain network? Well, I didn't think you could explain it. Fair enough. I'll explain it with has anyone heard of 6 degrees of Kevin Bacon? Yeah, the idea that Kevin Bacon is the center of the world in terms of Hollywood. He's actually not, but he's close to it. And the idea is that it's actually shorter than you think it would be to get from one node to the other. And this is the whole idea of 6 degrees of separation, that any human being is only about 6 or 7 steps from another human being on Earth. If you want to think that in practical terms, I would say, show of hand if you have a friend from another country. You probably all do. But just think of maybe the baker or some store clerk that friend goes to, and that store clerk's friend. Someone you will never meet, probably on another continent away, but you're only 2 steps removed from them. And again, this is a really interesting idea about, say, human society, especially after the merger of giant components, that we're not really that far apart from each other. And that, in fact, a lot of network theory is saying you're really not that far apart from other things that are in your connected network. And so this is that idea of the small world, that our networks are, and as you put stuff into a network analysis, you're not as far removed as you think you might be from other entities on the network. And as you do the things like between a centrality and pathing, you'll see that like maybe your networks have a maximum path of 12. That means you're only 12 steps away from the furthest thing on your network. Everyone with that so far? And so you know a little bit now about nodes, edges, paths, and distance. We've talked about that. We're going to actually get into some of the math and the operations, maybe the data that you want to get from network analysis. And these are all pretty basic terms and operations that most people want to see. Or if you're doing a network, they'll ask you, oh, what's your degrees? What's your density? And you'll be like, well, here's how I do it. So let's talk about density. This is the number of actual edges of your network divided by the total number of possible edges. And so actual connections against potential connections. So potentially everything could be connected on your network in theory, right? But it isn't necessarily. And this is one of our most basic measurements in social network analysis. And this becomes really interesting as things like epidemiology. We're looking at how does something spread in a network? How dense are the connections? The more dense they are, the more likely something is to spread. You can also think of this in terms of, like, say, information, conspiracy theories. How dense are the connections on, say, Twitter between people who are spreading conspiracy theories? This gets into those little, who's heard of media bubbles and social bubbles? I'm going to assume most of you have. This is that kind of idea. You have dense connections within these bubbles, but as opposed to maybe the network itself. And so you can actually do density of, say, components, and you can do densities of the entire network and compare how those are. Pythonic code, it's just one thing. You say, what is my density? And you get the result of, all right, you again, 1 is a completely dense network. So we're at like, what, about 7% of our total of possible connections. It's dense enough. In Gephi, again, you can do this by the graph density, and you hit run. And in this one, this is a different data set. You'll see that we are at 0.039. And you can copy and save it and print it out if you want. So that's a really easy way to say, this is my graph density. This is what's happening there. And given you'll expect over time that networks will become more and more dense as more people get to know each other, or as they actually start to collapse information-wise. Now we get into something called degree measurements. And this is where you start, and this is maybe what most of you are interested in. How can I identify what is important in my network? What is actually really critically, what are the big nodes? What are the big important people? And so in a way, this is activity or popularity, right? If you're more connected, you may be more popular, or you might be more useful to a network. There's things called end degrees. That's how many connections are coming into you, and out degrees, how many are coming out. And that's if you have a directional graph. An undirectional graph, you just have degrees, how many connections I have. And these can be weighted or unweighted. Again, if there's a really important connection, perhaps you assign weight to it. If you're just interested in what are the number of connections, perhaps you don't. For Python, you can always say, here's my graph, what's my degree? Then it'll give you right there what your degrees are. It's like Ned is connected to 57 nodes, Robert to 36, and so on. If we go back to Gephi, we can see our average degree, or we can run that, and we'll see degree distribution. This is useful. It tells you that one node is has a fairly high degree, and it kind of goes down rather rapidly. And then we go to your data lab, you will see the degree, and we can arrange it by that. So in our case, Edward Stark has a degree of 66. He is the most connected node on this graph. And we can go down to here that I don't even know who that is. Has one degree. He's just connected to one person. And so, does anyone know who Olaf, son of Umar, is in this story? I have no idea. And that might tell you, but we've heard about Ned Stark. He's played by, a famous actor. So there you go. Any questions on degree so far? And what's really kind of fun is that within Gephi, we have our stuff here. Let's actually change something up. If you see this icon, what does this icon look like to you? Go ahead and put in the meeting chat what you think this thing is. Wait, a telescope. Oh, size of the nodes. I mean, to me, it kind of looks like a croissant. And so it was invented by French sociologists, so maybe I'm reading something into it. I know I'm making myself hungry too. Sorry that this is before lunch. But this is actually changing the size of the nodes. So we can say it's unique, or we can do ranking. If we do ranking and we do degree, let's do a max size of a minimum size of 4 and a max size of 10. All right, well, let's do even better than that. And you can see you kind of play around. You have to see what looks good for your graph. And now you can see what happened. I've actually sized my nodes by how many degrees they have. So our more important nodes become larger. Now, does this become an easier graph to interpret now? I mean, let me expand it maybe a little bit. There. Does this become a much more viscerally interpretable graph than it does before? Yeah, you can see, oh, here's the important nodes. Here's where everyone's connected to. If I want to mouse over, oh, I can see, hey, this one's actually big because all these people are connected to Daenerys. Okay, she's probably important, maybe, in the story, right? Over here, who's this? Jon Snow. Yeah, he might be important. And you can also see where some of the components are. Who's connected to Jon Snow? These are all the Night's Watch people. And at this point, not really Daenerys or those people. So you can see how these kind of groups are forming and the degree measurement. And all we're doing is resizing it based on degree. And you can do the same thing within Python. And I have that actually in the notebook. You again have to play around with it, the parameters of it a little more than you would in Gephi, but programmatically you can do all of this. So that's degrees. What about centrality? And this is what a lot of people want to see. Who's central to it? Not necessarily who has the most connections. Where do you sit within the network structure? Are you someone who is really important that information has to go through or not? And this is the assertion that power is inherently relational. That if you are related to more nodes, if you are in a different area of the network than other people, you may have more power to this. And so this is the concept of betweenness centrality. And what it is saying, how often does a node appear on the shortest path of all the nodes in a network? So this is kind of an interesting concept. You could be really important, right? You could be a node where all the shortest paths go through you. So you're central, everyone's got to talk to you to talk to somebody else. Or it could be that you're at the periphery of multiple components. That maybe you could think of yourself, oh, functionally you're not as important in any one of these one components, but you are important in how they talk to each other. So if you think about, say, maybe different organizations or different parts of, say, a department or something, and you're the person who enables those communications, you're actually functionally extremely important because that's everything that's got to funnel through you to actually go to the larger world. Again, for Python code, we can say betweenness centrality, and that will give you the higher the number, the more central that you are. And we can do that again within Gephi. And we can say, you see, like we have all of our different kinds of stats here. Average weighted degree, diameter, density, connected components. And if you run all of these, you'll see that we have our betweenness centrality right here. And here, Edward Stark there's like, this is a massive number. That's showing he has the highest betweenness centrality. The lowest ones are these. Why do you think we have zeros for betweenness centrality? What do you think that represents? So we've got these huge numbers up here, people we recognize. What does it mean to have a zero betweenness centrality? Right, a node with a single connection. So if we go back to our overview, we're out here. This guy has a zero connection. Why? There's no shortest path other than himself to get there. He's not on anything else. And so these would be, if you see zero betweenness centralities, these are people who are very much on not only on the periphery of their component, they're on the periphery of the network. They're very weakly connected, we would call it, to the network itself. And so if you want to find out who is really just kind of on the outskirts of what you're looking at, a good way to do that is to find out who has your zeros, who is not being really that well connected to the network. And these are people who you could probably pull them out of the network, and structurally, the network would still exist. Structurally, a lot of that stuff would still happen, but they themselves, not a whole lot of stuff is going through them. That doesn't say they're not important. It's just to say that their connections aren't really there. The closest centrality is another interesting one. And this is the shortest path between all the nodes from a node. So basically, the idea is if you have a really high closest centrality, you're actually being able to spread information out fast. From you actually have a shortest path than many of the other nodes on the network. It's a little bit different than betweenness. And again, you can see it's closest centrality. You can do this in Python and get some numbers. And you can do the same thing in Gephi again. And you'll see that we have our closeness centrality. That again, you'll see sometimes the same nodes have a high betweenness and a high closeness, but not necessarily. And so what we'd say here is that these nodes are just simply on a lot of shorter paths so they can get information out very quickly. If we want to return back to our example of, say, social networks and things like Twitter or conspiracy theories, these are people that are able to get information out to multiple people very fast. So you would think of like maybe people with a very large out degree measurement would have probably a high closeness centrality. They're actually sending a lot of things out there. Does that make sense to people? Put up a red X if you're confused by it. Nope. All right, great. So those are two different centrality measurements. Here's the fun one. This is one I like because it's a different way of looking at connections. What if you yourself are not that important, but all of your friends are? Well, so that's it, or that you don't have very many friends. That but your friends are, say, the Pope, the president, and the CEO of Google. This is kind of what this is measuring. Eigenvector is that you are linked to important nodes yourself. So you can have actually a fairly high eigenvector centrality, but not be that central to the network. That means that you are friends with a lot of very influential nodes. And again, software does this for us. We do not want to try to do this by hand. And Python code, you'll get your result. And you'll see, again, for us, some of the main people are still there. And we can do this within Gephi. If we go back to our overview, and we can run our eigenvector centrality. And you'll see again that we have some fairly high ones and some fairly low ones. If we go to our data lab, we can arrange our eigenvector centrality. No surprise here, Ed is important because he has a lot of important friends. But same with all these other people. And you can see, oh, here, you can see, well, even though they have a smaller degree than this one, maybe this Faye has one or two more important friends than this person has. So it's an interesting way of saying what your relationship is in the network to not just to you yourself, but how important your constellation of friends are. And that's a concept that's pretty interesting. All right. And now here's another one called PageRank. And this is one that is pretty similar to eigenvector, but it also takes into account the weight and direction of connections. And this is used by Google. It's called PageRank from Larry Page. And so again, we can do this within Python and get our results. So just PageRank result. And we can do it within Gephi, which also has PageRank right here. And you can leave, most of the time you can leave these alone unless you're really into stats. The defaults are going to be good enough. And if you hit OK, you'll see, again, we have some that have very high page ranks, some that do not. And right there's our page rank. And again, some of the usual suspects, but you can see page rank is actually some of the people change. Like here, if we're looking at eigenvector, we've got Robert as number 2. But if we do PageRank, we have Tyrion as number 2. And so it's a different, again, what this is measuring is your eigenvector, but the direction and the weight of the connections as well. Eigenvector centrality is just connections, period. So if you're really looking at, again, taking account the weight and the things you want to see, you're going to want to look at that. And then this comes into something called bridges. And bridges are really unique. And this is where centrality kind of helps you. Bridges are basically where you have components that are joined. Oh, thank you. We just had some assistance. So now you can see that I'm actually here. Bridges are really neat because they're how you connect these disparate components. And they're fairly rare in social networks because generally as a network develops, people are going to get to know each other. The components are going to merge. And a single bridge, an actual bridge, is just one edge that connects people to another one. So again, very rare that you only have one person that connects to multiple groups. A local bridge is within a small area. Okay, here's one bridge that goes over, but maybe the components somewhere else have another bridge and somewhere else have another connection to the other group. Those are a little more common. And again, the best way to find this is betweenness centrality. Find who has the highest betweennesses, see where they are and who they're connected to. If you have a huge betweenness centrality, but a very small degree, you're probably going to be a bridge or a local bridge. Does that make sense to people? I hope. Yep, got some thumbs up. Fantastic. And if we're talking about the connections and things like strong ties, weak ties, and weights, You may say, well, I've been kind of squishy about that. I haven't really defined that because there isn't a strict definition when we talk about weights or strong connections or weak connections. It's really kind of up to you. You can say a strong link is a closer friendship, or maybe it's a parent-child relationship as opposed to, your colleague who sits across the hall from you or the person you see on the bus. It's really largely up to you how you define the weight of connections if you're thinking of them conceptually. And so you'll see people talk about strong ties and weak ties. Again, these are kind of fuzzy terms. And so how does this all work though? If we have ties, we have connections, we have bridges, what does this mean for the dynamics of networks? And this is an extremely important idea, this triadic closure. And the idea is that if you have two people in a social network or concepts or whatever, and they have a common node, so a common link, there's a likelihood that they'll be connected in the future. So again, to Game of Thrones, if Jaime and Pod start out as friends, and Jaime and Brianna Tarth are friends, and it's likely that Brianna and Pod will become friends, which actually kind of happened. And so you'll see it, this forms what we call triangles on the graph, right, of 3 different nodes. Think of Facebook's recommended friends, or say Twitter recommended accounts to follow. What's it doing? It's actually looking at triadic closure. It's looking at, oh, you follow this one, someone else follows this one, maybe you should follow this one. Conceptually, pretty simple, right? And that's what they're trying to do with a lot of these algorithms, is a little more sophisticated ways of looking at it, but it's still essentially triadic closure. And this is a basic function of a social network, and not an electronic social network, but an actual people social network. You know people, they know people, you'll probably eventually know those people. So a graphical representation of this, pretty simple, right? Any questions on that? Close to transitive. It's actually fairly close. Again, that you like here, you'll know someone, you'll know each other. Eventually, you'll form that link. So yes, Matthew, that is actually, it's very close conceptually to that. What you find with this is, if you're looking at things like triadic closure and bridges and this kind of thing, is the idea of embeddedness. That the number of common neighbors you have, and the more embedded you are, the more common neighbors you have, the more likely that triadic closure is going to happen. So basically, this also becomes a really interesting thing about social networks and how you perform within them. That if you have a lot of common edges with somebody, it's just easier to trust that person. You know a lot of the same people. You know a lot of the same kind of, maybe the same kind of ideas are going out. We talk about our media bubbles. You're all doing the same, you're looking at the same sources. You're talking about the same things. You're actually doing maybe performative things the same way. And what is really interesting about this is that actually helps form, if you want to think of group enforcement, that we say here, like, if you have a lot of mutual friends, you're probably not going to behave as badly or really maybe insensitively or attack somebody in that where you don't have the same number of mutual friends. You're going to have different ways of treating these people. And as you're building networks and as you're analyzing them, think about that. If you have 2 nodes that have a lot of shared connections, their behavior with each other might be very different than 2 nodes that don't have a lot of shared connections. So if we want to go back to say, who has ever worked a service job? Lots of us. What happens in a service job? You have customers who come in and they may treat you badly because you're not sharing a lot of connections socially with each other. Change that to say a more professional career. You may not have people behaving the same way to their colleagues there as they would for someone buying a sandwich. So there's different kinds of behaviors that happen, and different kinds of, say, social contexts that happen. And when you get, and you can again mathematically measure this, zero embeddedness means you have no one in common, and this is where it's fairly risky for interactions. Who has had a less than pleasant or honest experience with a used car? I'll put my hand up for that one. See one thumb up. Yeah. Why? Well, you don't, this is the only time you're dealing with this person. And so there's less social repercussions, say, for someone trying to, say, sell you a lemon than they are if they're trying to sell, say, their mother a lemon. So there's going to be different social repercussions for that. Now, the flip side of that, and this is actually kind of interesting, is that you can actually have very low embeddedness, but this can actually be to your advantage if you're within a network. It can be a structural hole that you are filling. That, again, different components. All these people interact with each other, but they have to go through you, for instance, or they've got to go through someone you're studying. Someone can actually use that to their advantage because they have access to information that other components may not have. Again, they're kind of a bridge between these, so they know things that maybe people in this component don't, or people in that component don't. And there's a lot of really interesting studies about people who occupy these positions, say in an organization or something else. They have a lot of different energy in reaching out to different groups. And so when you're studying this and you see, hey, we have low embeddedness, we have really high betweenness centrality, we have low number of, say, degrees, that's someone we might want to pay a lot of attention to, because they're fulfilling a structural hole in the network. They're connecting different components, and hey, they're really not connected to a whole lot of people themselves, but they're serving this very interesting structural role. And that's the kind of thing that you use, say, social network analysis in your data to find. Are these kinds of people that maybe your close reading doesn't identify? Or, hey, I'm looking at my lists of, in my case, ancient historians and prosopographies, and I'm trying to put together this network, and suddenly I discover here's some people that we generally don't talk about, but if I'm building my network, maybe this priest holds a really interesting position because he's connecting several cities and religious things together, but I wouldn't really figure this out until I built the actual network and the graph and did this kind of analysis to it. And so these are really kind of things to look out for, and things to be really cognizant of when you're doing your network studies. Another thing with this is that other issues when you're looking at these kind of people, these kind of positions are interesting for social gatekeeping, for instance. You actually might have people in these positions who are actively trying to keep triangles from forming. And so you might have people who recognize the position that they have and are trying to make sure that no one else does any connections to this. Some of you may laugh at that, or some of you may be laughing as you've met people like that who are like, oh, I'll take care of this. Don't worry about talking to them, and who really want to, occupy those positions. And this gets to a really interesting problem that they've talked about in, say, business administration, that the interest of a node and the interest of what that node is embedded in may not be the same. That perhaps these kind of networks or these kind of components, again, it'd be more advantageous for them to form and to merge, but it may not be advantageous for certain people within that organization to have that happen. And so, again, keep this in mind when you're looking at your graphs. Can anyone think of any examples of that or any questions about that? And you may say, oh, how can I find triadic closure? Well, it's really hard to find that in Gephi. There was something, but it broke thanks to free software. But you can do something called community detection in these. And what this is doing is trying to find where these connections of nodes are more dense with each other than other connections of nodes. And so this isn't perfect. This isn't necessarily finding all of your bridges and all of your other things. You're going to have to do the stats like I showed you to do that. What this does is give you a very quick idea, a very kind of overview of where are my more dense connections, who is more densely connected to each other in a general sense. And it's a really common practice to make this the color of nodes when you're doing a graph. And so I can show you here, like the Python code is this thing. There's different algorithms for doing community detection. This one is actually fairly nice, Boolean method. And what you do is you just make your graph like you normally are. But first you make this partition. And so this goes in and finds it for you. And then you can actually make, you can assign to colors, draw your edges. And when you show it, you'll see these different groups forming. And so what's showing is that this color is more densely connected to each other than, say, the yellow colors. That's how you do it in Python. Again, the notebook can see. But if we do it in Gephi, we just run our modularity. And again, default values are fine for the most part. And you'll see that happens. We go to our data lab. you'll see it's formed our modularity class. And we will use, this one actually makes sense, the color palette. Then we'll say a partition based on our modularity class. And now how does that graph look to you guys? Is this now a much more pleasant graph to look like and something that communicates? Oh, there's a big heart. Someone loves this one. This is what have we done? We just put in our edges file, ran a few stats on it, and said color it by our modularity. And what do we have here? We have something that really does communicate effectively to people. This is not that huge, horrible graph that we saw at the start, right? This is something that is very much showing you, like, here's the red group, here's the purple group, here's the green group, here's the blue group, and you can get into, again, you can filter, you can say, hey, what class do I want to see? Filtering in Gephi is sometimes a nightmare, so we're not going to try it too much. But you can see here's my graph. And if you want to export it, you go to preview. And you have options here, so we can show labels. We can expand things out. We can say, oh, let's rescale weight. And we can say, oh, wait, a minimum of 1, a maximum of, say, 4. And there you go. And you have a graph that's actually suitable for printing. We can go to our overview and say, hey, let's expand it a little bit more. And there you go. And you can do things like shorten your labels. And you can actually export this out into, say, Adobe Illustrator or an SVG file. And then you can keep everything where it is and just, play around with your labels and move them around a little bit and have a fairly nice, beautiful graph to throw in your publication, your class, or what have you. So there you go. That's kind of the general overview that I wanted to show for this thing on network analysis. Again, all the tools are there. I will go back to the first slide, and you can find the link to this entire presentation, which will have all the links, the code, and everything else in there. So there you go. There's the QR code, which will give you the link. So any questions? Anything that you want to maybe talk about in a little more detail? Anything about social network analysis that you're interested in? You can do things. And why I brought Python is that you can do really amazing things in Python with this kind of data, that you can do things like a social network analysis that is geospatial, for instance. I can show you one that I've done a while ago, so you can do all kinds of scary, interesting things with network analysis. Let me just share the screen on this one. So for instance, this is one where I put everything in Python, found out my different kinds of nodes of which cities were mentioned most in a source, put the nodes, because they were cities, I knew where to put them geographically, used a route network, which was Roman roads, and then those are sized by the number of paths that went between them, creating a different kind of view of, in this case, what I think how we should be representing ancient kingdoms. And so that's all this is network analysis put into a geospatial context. And so you can show, again, all kinds of really interesting work just by running this kind of code. And just by you can go from here to here actually fairly easily with only 1 or 2 more steps. So any questions, thoughts, ideas? Nope. Well, again, I'm here at OARC. I am happy to help you in your exploration of graphs and charts and network analysis. So if this is informative, please let me know. If you want to know more about it, let us know. And if you'd like maybe additional workshops on taking network analysis to another level, like maybe focusing more on Python or focusing more on even more in-depth network change over time or displays or anything like that, please let us know. With that, I believe it's noon. It's probably time for everyone to go have lunch. And I definitely don't want to get between a workshop and lunch. So with that, thank you everyone for attending and have a nice day.